my talk. I'll be talking about fractals and broken dimensions. So I'm a PhD student in Switzerland at the University of Fribourg, but I'm here for the semester visiting. And my research lies sort of in the area between geometry and analysis. So I work with metric spaces and do something called analysis of metric spaces. And what has sort of gotten me into this field are fractals. So when I was an undergrad, we had to, in my university, we had to write a thesis in the end. And I don't really know why, except because fractals are beautiful. I guess.
We might have to turn it off.
Yes. Oh yeah, nice. Yes. So I just wanted to do something with fractals. And so here are some examples of things that can be mathematically described as fractals, which we find in nature. And maybe a question is, what do you think these pictures have in common? Or what is a common sort of theme when you look at these things? Any ideas?
Self-similarity.
Yes, the self-similarity. And also here, so those are a few examples of mathematical, more mathematical fractals. And as you said, so what is self-similarity? Self-similarity says that when I zoom into one of these pieces, it looks exactly the same as the whole thing. So it's self-similar. And this also holds for, like in nature, so here, this thing, it kind of looks like the whole. And all of these are. And you can even zoom further in, and it looks like the whole thing. So that's one of the attributes that fractals can have, is they can be self-similar. Not all of them are self-similar, but those are sort of the easiest fractals to study. So how can we construct these objects? And one way of constructing it, I'm going to show it, is sort of iteratively. So maybe you've seen the counter set in some of your lectures, I'm not sure. But what we do is we start with an interval. So usually the interval 0, 1. And we can delete sort of the middle third of this interval. And that's our first step, C1. And we continue doing the same thing. But instead of deleting just the middle third, we do it in each of the sub-intervals. And we continue and continue and continue. And in the end, the counter set is defined as the intersection of all of those sets. Now, this is you can think, well, that's nice, but why would one be interested in these sort of things? And the counter set has many nice properties. So first of all, it's an uncountable set. But the measure of the set, so the Lebesgue measure, is 0. I'm not sure if probably not all of you have heard of the Lebesgue measure, but it says that the cardinality is the same as like the interval 0, 1 itself, but the measure of it is like nothing. So that's very nice. And also it gives rise to very nice examples of things. For example, so that's something called a counter function, which is again defined iteratively. So on sort of the thing you delete, you put the function constant, and in the sets that you keep, you just increase the slope. So it maps still, so it's sort of surjective on 0, 1, but it is constant everywhere but on C, on the counter set. And it's a continuous function. One can show that this is a continuous function, but in some sense it maps like a set of measure 0 to a set of full measure. So that's a function, by the way, it's a function that is continuous, but not absolutely continuous. If you ever need an example in like an exam, that's a very, very nice example. Okay, so there are other fractals. One of them, which is also quite famous, is the Koch-Snowflake curve. And again, we start with the interval 0, 1. But now, instead of sort of just deleting the middle third, we replace the middle third with two intervals, also of length 1/3 of. And then instead of like what we do is we replace each of the straight line segments with a scaled version of that, of K1. And we can continue to do that, and you can also see where the name comes from. So Koch is just a mathematician, but Snowflake is really, it's sort of already after the fourth iteration, it starts looking like a snowflake. So before, what we had is that the counter set then was just the intersection of all of these sets. And here it's less obvious how we should define. So we want to do that infinitely many times, but how do we really define whatever we have in the end, right? Okay, so that's my second example. I will talk about the third example, and that's the Sierpinski triangle. So here, instead of starting with the line segment 0, 1, what we start with is a triangle, so it's something two-dimensional, and we delete sort of the middle part of this triangle as there, and we continue to do that, and we keep only like the black set. So this again we can describe as an intersection of all of the sets before, like the counter set. Now what can we observe? So instead of deleting things, we can also say that we scale it and sort of shift it. So we start with maybe let me draw that on the blackboard. So we start with this triangle. Okay. And then what we do is we scale it. So we make it half as big. And one we map here. One we map here, and one we map here. So that's whatever we keep. Okay. So we have 3 maps. Okay. And what I claim now is the following. I claim that this Sierpinski triangle is the only set which is sort of a fixed point, or it's a set that if I apply these 3 maps, or just the union of whatever the image is, to the Sierpinski triangle, it will stay the same. So what you have here is, when this is my set E, then this is, oh, now I have to order, this actually is F1. So that's F1 of E. This is F2, and this is F3. So that set here is F2 of E. F3 of E. But here, these 2 sets are clearly not the same, right? But if you would start with that one, or like the infinite iteration of it, then what you would get is exactly the same set again. Can you sort of understand?
What about taking a bigger Sierpinski triangle? If you take a Sierpinski triangle that is twice as big, shouldn't it also weigh the same property?
Then you would have other maps, or yes.
Okay.
I mean, it depends on which set you start with.
Okay, okay,
But yeah.
okay.
Yes. I guess if you have something bigger, then you need to shift it more.
Okay, that makes sense.
Good. So it's actually, yeah, it really is unique, and we'll see that in a second. Okay, so how do we do that, like mathematically more than just in a picture? So what we need are maps that are called contractions, or also like one-digit maps, or they have many names. But anyways, so what we want is that we have some constant L, such that two image points, they have distance less than equal to L times the distance of the original points. So we want that this distance here is strictly shorter because we choose L strictly less than 1 than this distance here. That's why it's called contraction. Now, if we have an equality there, then we're calling it contracting similarity. And this will be important later on. So the concept is clear, we just shorten all the distances by some factor n. Okay. Now, if we have a closed set in R2, most of the time I will just take R2, for when we could do it with a closed set within it. And then we call a finite set of contractions, we call iterated function system, or just IFS. And if we have such an IFS, we can sort of define an operator F on compact subsets of D. So this is just to make notation easier. So that's what we do here, right? We don't only consider the image of like one set, but we consider the union of the set, right? That's what is interesting. What is interesting to us, and that's also what is described here. So we have these F1 to Fk, and we consider the union of like the images when we insert in sets. And we can also do this ith iterate of F. So we start with just here, this is 0, then that's F1, and so on and so on. Right. Okay, so that's the notation. And then what is defined in the literature as an attractor of an IFS is whatever we had before with this Sierpinski triangle. So if we have that the set equals F of this set. So that's what the sort of property, what we're looking for, and that's whatever our fractal is about. Good. So that's sort of setting the stage. The theorem is the following. So for every iterated function system, there exists exactly one attractor. Okay. And if we have this condition here for every compact subset E of R2, or D, whatever we have there, so this says that we sort of map into the same set. So here that's the case. Yes?
Sorry, I missed. What is an attractor?
An attractor is this thing here. So when it's sort of mapped to itself by F, this operator F. So it's the fractal we're looking for. So then, this is actually given by this intersection. So the counter set, and also this example here would be something that we get. Now, I want to prove that. Just maybe very quickly, and the proof uses Banach's fixed point theorem. Maybe you've seen that, maybe not. Okay. Before we prove the theorem, I want to define the following thing. So, yes?
is the right-hand side of the first theorem maybe evaluating in E rather than A? Is it well written?
What do you mean?
Wouldn't it make more sense to make the intersections of F of E?
Oh, yeah.
than of A?
Yeah. You mean here?
Yeah.
It's an E, yes.
Okay.
Thanks. Yes, that's the same. Other questions? Okay. So, if, let's call them B and C, so we have two compact subsets. That sort of Hausdorff distance the range is defined supplying the edge of BC. Maybe I'll draw the picture. So we have the set B here, and we have the set C here. Okay. Now the Hausdorff distance, it's the minimal delta for which we have the following, namely B is contained in a neighborhood, the delta neighborhood, meaning that around every point of C, I sort of look at the points which are delta or whose distance is less than delta to some point in C. So the delta neighborhood of C maybe looks like this. So I want that B is contained in the neighborhood of C, and similar, on the other hand, I want that C is contained in the neighborhood, delta neighborhood of B. Okay. And we should look for the minimal such delta, so maybe here we have some neighborhood and delta of B. Now, if we have points, if that's B would be a point P, and C would be a point Q. So that's an example. What we have is the delta neighborhood is just a ball of radius delta around the point. So this here is actually the distance. Would just be P minus Q times the value. Okay. So but then for bigger sets, it's sort of the analogous sort of statement for. Okay, if we have that, so we can also we can prove theorem. So that I denote by C is the set of compact subsets of R2. Now, C, equipped with this distance dh, is a complete metric space. Okay. You can show this that sort of if you have sequences of Cauchy sequences with respect to this metric, of sets which converge. So if you would have, for example, maybe you have like balls of a certain radius, which get smaller and smaller, or it converges to some ball, then the limit is in the set. So it's again a compact set. So you have that this is a complete metric space. And what we can observe is the following. If we have CH, now of F of B and F of C. So by definition of F, this is the H of the union of Fi of B and the union of Fi of C. Okay. Now, I'm kind of following. I claim that this is less than the maximum of 1 less than I less than M of this. Okay. Why? So if I have that, if the delta neighborhood of Fi of B, if this contains Fi of C for any I, then we have to have that the delta neighborhood of the union this also has to contain the union of this Fi. Okay, so that's why we can say that this has to be less than the maximum. Now, every Fi was, we assume that this is a contraction. Okay, and so in particular, what we have is that Fi of B that this is less than the distance between or less than Ci. Yeah, I actually got one. So F of B and F of C, this is less than the maximum over all of those Ci's. Of the distance of B and C. Okay, so because we scale all the points, this has to hold. And this thing here, that's an element of 0, 1, because C1 or Ci wasn't 0, 1 for every I. So we have shown that this is F is sort of a contraction on this space C. Okay. So having that, we can apply this Banach's fixed point theorem. We can apply the Banach fixed point theorem to find a fixed point. Now, fixed points in our sets are sets, and this will be our attractor. And the second part of the theorem actually also comes from Banach's fixed-point theorem because it also gives you, I didn't say it here, but it also gives you sort of a sequence which converges to this set, which is exactly what we want. Okay, so far so good. So that's about this theorem. Now, going back maybe to see a few examples, and here this is the example we already seen of the Sierpinski triangle, which is the adjunctor of this iterative fractal system here. And maybe you can figure out the maps for this fractal. It's a bit more complicated. So we have one that just scales it into 1/3, and then we sort of have to turn it. That's the second one. The third one, we have to, and shift it as well. This one as well, we have to turn it and shift it. And the fourth one, which is scaled by 1/3 and shift it. Is this clear? Good. And also the third example that we've seen is the counter set. And here we just have 1/3 x, and then the other one is 1/3 x plus 2/3. Good, so far so good. So now what I want to talk about is our dimensions. So in some sense, so we can think of these objects, or think of what should their dimension be. Because in our construction for the Sierpinski triangle, we started with something two-dimensional, right? So we took this triangle, this is two-dimensional. But then we always take something out, okay? And the question is sort of, in the end, what's the dimension? Because maybe we took so much out that it's only one-dimensional. Or if we go to the snowflake curve here, we start with something that's one-dimensional. But in the end, we will have so much wiggling that it's sort of, maybe it's more than one-dimensional, depending on like whatever notion of dimension we talk about. And one of the notions of dimension which sort of captures this fractal behavior is something called box counting dimension. And it's quite easy to explain how it is. So the name of the thing already tells you what we do. So we have a figure in a plane, and we choose a number, and we make boxes. Okay? And these are squares of length 1/n. And we count the squares. Now, the beamer really is not very good, but we count the squares which touch this set, and this gives us a number, depending on this side. So here, for example, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we increase little n, so we have sort of a smaller scale, but we will get more numbers. This will grow, and we continue to do that. And you also sort of see that sort of these boxes, but they approximate the set that we had in the beginning. Now, the box counting dimension is given by the following formula. So we have this number of boxes that we count that intersect our sets, and we divide it by log n. And this is our box counting dimension if this limit exists. Okay. We do an example. So we have some segment of some length L. Maybe here in the example, L is actually like 2.2 or 2.1, something like that. And we start with n equal to 2. So we touch 5 boxes. So it's log 5 divided by log 2, and this gives us a number, which I already computed. And we continue, so if n is to 4, it gives us log 9 divided by log 4, and so on. And you see that here we can ask ourselves what is it in the limit, and I claim that in the limit n of n is more or less the length times n, okay, for whatever length we have. So that's more or less this here, so log L times n divided by log n, which we can reformulate by all the logarithm rules to this one thing here, okay? So this should be true. The larger n gets, the better this approximation is. And so if we let n now go to infinity, but L, that's a given number, so that's safe space. This term here will go to 1. So we have that this box counting dimension of this set E here is just 1, which is reasonable, right? We have a line, we want something one-dimensional. So that's good. Let's do maybe another example, the Sierpinski triangle. We can again do the exact same computation. We make squares of like 1/2. So here I started with a Sierpinski triangle which has height 2, I guess. Yes, we count the number of squares which we touch. So that's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And we continue in this fashion here again. But since we're self-similar and we've sort of chosen this well, so the scales, it will always be the same. Now, why this 9 here comes from the fact that I have 1, 2, 3, 4, 5, 6, 7, 8, 9 of these smaller copies in this next scale. And we can continue to do that. We get this sort of formula, and we can compute whatever the box counting dimension is. And it turns out it's logarithm 3 over logarithm 2. So that's just by inserting into the formula before. Now this gives us a number which is 1.58. So it's what I said before, sort of it's between 1 and 2. Okay. Good. Good. In general, one can do that even more nicely. And we say that an iterative function system it satisfies something called the open set condition if we find an open set such that f of u is again contained in this open set. That's sort of technical, but if our IFS satisfies this, then we have actually that this box counting dimension is given by the following. So if we have k, so that's the number of functions in the IFS, and they are similarities, so they decrease. We have an equality in this formula that we had in the beginning. So every 2 points, so the distance between fi of x and fi of y, so that's exactly c times the distance between x and y. Okay. So that's the contrasting similarity. And if we have that, then we can actually compute this box counting dimension with this exact formula here. Yeah, so this condition sort of tells us that the maps, they shouldn't overlap in some sense. Now, we can go back to our examples. So for the Sierpinski triangle, we have had these three maps and we compute them, they all scale with a number of 1/2, okay? And we have three maps, so three contractions which shorten the distance by a factor of 1/2, and therefore we have that box counting dimension, logarithm 3 divided by logarithm 2, and the minus cancels the 1/2. Rearrange things. Okay, so that's maybe something to note here is that we could also construct the exact same set. Instead of starting with something two-dimensional, we could also start with something one-dimensional and sort of go from there and increase the dimension. And that's what I drew here. So we can also get the Sierpinski triangle by the following. So we have this line segment 0, 1, and we make it, we scale it by a factor of 1/2 and sort of make this shape here. So we take three maps, which are all shortened by this 1/2, and we sort of turn the set, and then we replace each straight line segment by something like this, and continue in the fashion. And it turns out that in the end we get the exact same thing. So that's, I think, really nice that you can also sort of for these map or this set with a dimension between 1 and 2, you can also start the other way around. I sort of adding more. And you see why this should also have this exact same dimension. Good. Yes. So we can actually, a few exercises here, but probably, yes. So for the counter set, what we have is we have two maps, both scaled 1/3, so that's just logarithm 2 over logarithm 3. And yeah, the Cox snowflake, we have 4 maps, which scaled by 1/3. So we have this, and this is another set, which I quite like. But anyways, yes, I guess that's already what I wanted to say.